Okay, so today we're covering work and energy. The first section will be covering work, okay? We'll go through a definition of work, talk about the relationship between work and kinetic energy, work done, work in 3 dimensions, power, and then an example. We then cover energy, okay? So we've got potential energy, kinetic energy, what constitutes mechanical energy, and then conservation of energy. And then we've got something called the energy methods, okay? And the principle behind that, the energy balance equation, and we'll go through an example of those as well. So, if we imagine a particle lying in 3-dimensional space, okay, the work required to move the particle from point A, arbitrary point A, to point B, is this thing here. It's the integral of the force times by the change in its displacement vector. Okay, these are 2 vectors. We know what this is. This is a dot product. Okay, we covered that in the first lecture. We know that a dot product comes out as a scalar, which is why work is written in italics. Work is not a vector; it is a scalar. And F is the force required to move the particle, and R is the position vector indicating its displacement. So I've got a particle here. I apply a force, okay, and if I apply a force from here over to here, okay, the distance we moved we know, and the force we know, then we can work out the work that I've done to move that particle. It's often a lot easier to, when we're dealing with this stuff, is to look at it just in 1 dimension, okay? So I've got point A here, point B here. This is my positive x direction. We're dealing in 1 dimension. I've chosen x. It could have been y or it could have been z. And the work required to move the particle from A to B is the integral of the force times the change in distance, okay? And the unit of work is joules, okay? Well, obviously force we know is newtons, distance we know is meters, newton meters. They're the same thing as joules, okay? And a joule is what we use for work and energy. We use newton meters for moments and torques, but we'll discuss that later. We use joules for work and energy. And so if we take Newton's second law, okay, we know F equals ma. And we know that A is dv by dt, v dot, yeah? This is the change in velocity over the change in time. And we also know that dx is v times dt, okay? Obviously, v is the change in displacement over the change in time. I can rearrange that. Dx equals v dt. Okay? And so what we can do is we can substitute these things in here. We know we had work is force times distance, okay? Or for f dx, okay? So we've replaced force with m dv by dt. That's there. And we've replaced dx with v dt. And the dt's, you've got one on top and one on the bottom. They cancel each other out, so you end up with mv dv. Okay? That's the integral between va and vb. And then if you integrate this term, mv, you get 1/2 mv squared. Okay? Obviously, between va and vb, you get 1/2 mvb squared and minus 1/2 mva squared. And we all know what 1/2 mv squared is, don't we? Anybody? Kinetic energy. Yeah, exactly. So we know the work required to move a particle from point A to point B is its change in kinetic energy. So as we discussed in section 5, the term 1/2 mv squared is known as the kinetic energy. And so the work to go from A to B is the kinetic energy at B minus the kinetic energy at A. Or mathematically, WAB equals UKB minus UKA, which is delta K UK. Okay? And this is known as the work-energy theorem. We've got work on one side and energy on the other. Now, so this is the relationship between work and kinetic energy. What about work done? Well, if we've got a constant force, obviously, we take the definition described at the start, okay? Obviously, because the force is constant, you can just take out the integral, okay? If force doesn't vary between A and B, then basically the work done is the force multiplied by the distance, xb minus xa. Obviously, if you set xa to be 0, then it's f times x, which is pretty simple, straightforward stuff. Okay? So although we've got this ugly integral sign, integrals, it's actually quite easy just to simplify it out and get rid of the integral sign. So work done is force times distance moved, F delta x. What about work done against gravity? Okay, here we've got a particle, okay, and it's moving between A and B through a height h, okay. And we know if the force is going to overcome gravity, then F equals mg, okay. F, sum of the forces of this particle, ma, okay, equals F minus mg. If it's not accelerating, let's assume it's constant velocity, then A is 0, and you have F equals mg. And so, if F is the force, it's mg, okay, it moves through distance h, okay, force times distance is the work, then the work done is mgh, okay. Now the work done by gravity, obviously the force of gravity is minus mg, and let's assume you had a particle at B, and you let it drop under gravity, then gravity does work, okay. We said y is positive in the upwards direction, so the work done by gravity is negative. As we said, work is a scalar, so it can be positive, it can be 0, and can be negative. Now, I've got my box here. This introduces the idea of network. And if I'm holding the box up, I'm doing work on the box. If I lift the box, I'm doing work on the box. If I put it on the ground, gravity's done work on it, okay? If I lift it up again, I've done work on the box. If I've dropped it, there's been negative work, okay? Positive work, negative work. Positive work, negative work. I could do this all day, and my net work would be 0, okay? Positive work, negative work. I'd get very tired, and you don't want to confuse getting tired with doing work, but work would have been done, but the net work, okay, would have been 0, okay? Obviously, I'm applying mgh to lift the box up, okay? And then gravity is doing minus mgh to pull the box back down again. And you add those two together, you end up getting 0, okay? So net work can be 0, okay? And at the moment, the table is doing work to keep the box up. Obviously, if the table wasn't there, gravity would pull it down. And then the ground would be doing work to keep the box up, okay? So, what about the work done against friction? Okay, well, we've got a block here. It's moving from this point to this point, which is a distance delta x, okay? There's a force being applied here. And obviously, there's a frictional force in the opposite direction, which we know is the coefficient of friction, mu, times by the normal force, n. And in this case, n equals mg, okay? And so we know what everything is around here. And so the force being applied has to overcome the friction force, okay, which we know is mu mg, n is mg. And so the work done is that force times by the distance, so we have mu mg delta x, okay? What about something that's done by a gradual force, okay? Work done by a gradual force. We've got a force here that varies proportionally with distance, okay? So from at point 0, there's no force, okay, and at point x, there's some force F, okay, and basically we know that force times distance, okay, is the area under the graph, okay, and so obviously the average force here is 1/2 of this, 1/2 F, and you multiply that by the distance you travel, and you get the work done by a gradually applied force. Now this is pertinent to the work done by a spring, okay, because obviously you have a spring in its relaxed position, okay, and you start to pull it. It doesn't take much force to start it going, but the moment you pull it a very long way, okay, the force that you need to pull it is a very, very large force. So this is a very similar type of situation, okay, as force is with a very small extension of the spring is very low, but as you pull the spring further and further away, the force, the spring force that's required to return the spring to its initial state, okay, is very high. And so the spring force is very similar. We have F equals K times X, okay, where spring is the stiffness, okay, and we know that that F varies with respect to the distance, okay, and so we've got 1/2 times by the force, okay, 1/2, if you remember from here, we've got 1/2 times the force, Well, if we know the force is kx, and 1/2 kx is the force that's being done, okay, which is a gradually increasing force. Multiply that by x, which is our extension, we get 1/2 kx squared, which is the work done against a spring or by a spring, depending on where you're looking at it. Now, in 3 dimensions, okay, work can obviously be in one dimension, more than one dimension. Here we've got a point A and point B, and this is the path that the particle between those two is taking. And if we choose a very, very small segment, dr, and the force is in that direction, okay, which is not in line with the direction, okay, then we can use our equation this is the equation we had at the beginning, the integral of the force time with the dot product times by dr, okay? Perhaps this is easier to understand if we take it in 2 dimensions, okay? So here we've got a mass m moving between here and here, okay? And the force this time is not in line with the direction of travel, okay? The force is at some angle to it, okay? And you'll remember that we've got our dot product in there. And if you remember that the dot product, the magnitude of the force, okay, was the magnitude of the force F, okay, times by the magnitude of the distance, F dot dr, okay, times by the cosine of the angle, okay, which is obviously, the cosine of the angle is this component of this force, okay, that's the cosine of that angle. And so, there's our work, okay, magnitude of F times the magnitude of R times by the cosine of the angle, okay. And we can decompose these vectors F and R. Obviously, that's standard vector decomposition using ijk notation. For fxi plus fyj plus fzk, okay? And dr is obviously going to be dxi, dyj, and dzk. And if we plug those equations back in, okay, we've got the derivative of work, we know as f dx, f dy, and fz dz. And if you take the integral of one of those things, the integral of that, okay, we know is the change in kinetic energy. We've done that already, okay? If you replace f with m dv by dt, okay, and dx by v dt, you end up getting the change in kinetic energy. We can do that in the x direction, the y direction, and the z direction, okay, to give us the work. And so the work is basically the kinetic energy in the x direction, the change in kinetic energy in the y direction, and the change in kinetic energy in the z direction. And obviously you can regroup them into vectors, and we end up having work between A and B is 1/2 times m times by Vb squared minus Va squared. The work is the change in kinetic energy. So that's work. We then have something called power. Power. And that's basically the rate of doing work. Okay, we have the work done divided by the time it takes, and that gives us what we know as power. And that leads on to something else, which is quite nice. We know work is force times distance, okay? And power is force times distance divided by time. Well, if we ignore force, yeah, what's distance divided by time? It's velocity, yeah? So power is also the force times the velocity. And so, if you remember back in, I think, lecture 4, where we covered non-uniform acceleration, you remember that the aerodynamic drag for a car was some function of v squared, do you remember? Okay. Well, let's assume that our car doesn't experience rolling resistance, but is under the effect of aerodynamic drag, okay? Well, the power produced by the engine that's going to give you the force, okay? If you know the power that's given by the engine and the force that's produced by aerodynamic drag, you can find the top speed of the car, okay? So power gives you that top speed. The same with Bloodhound. They've used a very complicated version of this, okay? You've got Bloodhound, it's producing however many newtons of thrust from the rocket and the jet engine, okay? And there'll be some force that it's got to overcome. That is a bit more complicated than the one I showed you because it varies with speed in quite a complicated way. But essentially, if they want to achieve 1,000 miles an hour, okay, they've got their V, and they've they know the shape of the body, so they can work out F. They need to know, they can then find out how much power is required to send Bloodhound along on its way to 1,000 miles per hour. Okay, and it just so happens that that equals what a Eurofighter jet engine produces and a rocket produces as well. You add those together, you should get enough power to reach 1,000 miles per hour. And the unit for power, you may have heard, is watt, okay, or kilowatts. Okay, and 1 joule per second is 1 watt, okay, which also equals 1 Newton meter per second as well. So that's power. Now, I do have an example for this, okay. It's on page 89 in your notes, okay. I haven't got the visualizer. And it says that, that's interesting. That's not what I've got here. Please stop. There we are. Right. That's better. Okay, so I've got the problem we've got is here. I'm not showing you the whole page because I've got the answer down there. Okay. I've got a mass at this point that's sliding down this shaft, okay, under the force of gravity. We'll ignore friction, okay. And the position, we've got the position vectors. We've got R1 and R2, okay. We've got our mass, 0.5 kilograms, and we've got the velocity at 0.1 meters per second, okay. And so it says, what is the work done by gravity on the mass? And so we know work, okay, between 0.1 and 2 is going to be the change in kinetic energy. Okay, so that's the kinetic energy at 2, UK2, minus UK1. This is ignoring friction, okay? We know that UK2 minus UK1 is the integral of the force between 1 and 2, times by dr. Okay, these are vectors. And we know the force applying on that mass, okay, that was heading down the shaft, mg, okay, because it's heading downwards. And obviously that's minus because we've said that positive j is in the opposite direction, so that's minus mg j dot product of R2 minus R1. Okay. Now we've got R2 and R1, they're given in the question, so we can replace those in here. We've got equals minus mg j times by, we've got 5i plus 2j, okay, minus 2i plus 5j. Okay, so we've got that. And obviously, we can just group the i's and j's together for the r to get dr minus mgj. Okay, so we've got 5i minus 2i, so that's 3i. And then we've got 2j minus 5j, so that's minus 3j. Okay. And if we put this j through on this side, we've got minus mg times by 3i dot j, okay, minus 3j dot j. Now what's I dot j? No, that's cross products. I cross j equals k. What's I dot j? Do you remember? You've got two perpendicular vectors. What's the angle between them? 90, okay, and what's the cosine of 90? 0, okay, cosine of 90 is 0. And so I dot j is 0, okay? So that term just drops out. Gone, 0. And so we have mg times by 3, j dot j, cosine of the angle between them is obviously is 1. Okay, so we don't need to worry too much about that. And we end up with mg times 3, so that's going to be 9.81 times by the mass, 0.5, times by 3. Okay, and that comes out to be 14.715 J. There's the work done by gravity on that point. Okay, so this is just very simple. I've forgotten the dot up there. That's a dot, by the way. Yeah, it's very simple vector manipulation, basically. Okay. Right, that's good. Okay, has everybody got this down? No? Yell if I've... Okay, so that's work. That's yeah, work. Right. Now, energy. Energy, we know, is the capacity for doing work. Energy is the capacity for doing work. And there are 3 mechanical energies that we're going to study here, okay? That's gravitational potential energy, elastic potential energy, and kinetic energy, okay? They're the 3 that we're going to talk about. And quite simply, if work's going into doing something against gravity, then the gravitational energy is going to be the work that you put in against gravity, okay? The same with elastic potential energy and the same with kinetic energy. Essentially, again, we've got our situation with gravitational energy, okay? And as I said before, if I do work to increase the energy from point A to point B, okay, I've given this block M some potential energy. And so, if we know that the work done to move the block from A to B is mgh, then the potential energy in this block at point B will be mgh, okay? If we assume that the block, let's assume this is M, okay? And on the floor, potential energy is 0. If I lift it up to this point, okay, I've done work on it to raise it up. The amount of work I've done is mgh, okay? And at this point, the potential energy in this thing is mgh, okay? And if I wanted to if I drop this block, obviously, that's converting that potential energy, mgh, into kinetic energy, which we'll cover in a second. So the work done to move from A to B is mgh, and that is also the gravitational potential energy. With a spring, we know the work done by a spring is 1/2 kx squared, okay? Well, the elastic potential energy is 1/2 kx squared, okay? It's the same thing. Because the work you do to compress a spring, obviously that energy, energy that you've applied, the work that you've applied to, has been stored as potential energy in that spring. So you release that spring, it's got that much energy in it that's it's going to apply to whatever you release. Kinetic energy is the energy stored in the body by virtue of its velocity, okay? Again, it's a scalar, and it's independent of direction. And the work done to move a body has gone into increase the store of kinetic energy within the body. And that obviously equals 1/2 mv squared, which we saw before. And so like I said, you've got a block, you drop it. Here it's got potential energy, it's not moving, so its kinetic energy is 0, okay? And if I drop it, the point at which just before it hits the ground, it's got maximum velocity. And that's the maximum velocity, that's been converted from the potential energy, okay? So the mechanical energy is those potential energies all added, or those energies all added up together, the potential energies and the kinetic energy. And so that's the U, the potential energy of gravity, the potential energy in the spring, and the kinetic energy. You add those all up together, that's called mechanical energy. And conservation of energy means that any sort of energy, okay, can neither be created nor destroyed, okay? You can't create energy from nothing and you can't destroy energy. But it can be transferred from one form to another. Now, we talked a little bit about this when we talked about conservation of momentum, or when Neil talked about it, in the sense that you can't create energy, but it can be converted to some other form. And although conservation of momentum must be maintained, the conservation of kinetic energy doesn't have to be, but the conservation of energy also has to be. And so that loss in kinetic energy that you get with an elastic or inelastic collision, you'll get another form of energy out of it. So that could be sound, it could be heat or whatever. And there was a problem in the momentum section of a ballistic pendulum where you looked at both energy and momentum, and that was an inelastic collision. The bullet went into the block, the ballistic pendulum, and that bullet implanting itself in the block of wood creates heat, which is a form of energy, thermal energy. And the other example is a falling body, that's the one I was just talking about, loses the potential energy as it loses height, h is reducing, but gains an equal amount of kinetic energy as the speed goes up, v increases, h is going down, So, the last bit is energy methods. And energy methods helps us in solving complex problems where using Newton's second law stuff could be a bit more complicated than we need it to be, And what you do is you look at your system. That could be a quarter of a car, the suspension system, or just some spring system, something like that, And you look at it as one entity, You have kinetic energy in that system. You've got potential energy in that system, And the two arrows, you've got work going in, so the work gained by the system and the work lost by the system. And we can apply an equation to this, an energy balance equation. Well, we'll go through these first. The work gained is the energy gained by the system as a result of work being done. The work lost is a result of work being done by the system on the surroundings. That could be friction, for example. We've got the kinetic energy stored within the system, so that's by virtue of its velocity. And the potential energy stored within the system, which could be due to gravity, could be due to a spring. And we know from conservation of energy that work can only be created, work cannot be created or destroyed. It can only be transferred, And so by equating the two sides, we've got the kinetic energy at one point and the potential energy at one point, plus the work gained between those 2 points, minus the work lost between those 2 points, must equal the mechanical energy at point 2, This is known as the work energy balance. Energy balance equation. Right, now we've got another example that I'll go through. There we are. This time I have got the sheet. Okay, so there it is. Let me move this forward a bit. Okay, so we've got a says a mass of 200 kilograms, M1 is connected by a rope over a pulley to a mass of 400 kilograms. Initially M1 is held in position, and then it is released and allowed to slide over the horizontal surface. The coefficient of friction is 0.2. What is the velocity of the masses when they move 2 meters from their starting at rest? What assumptions have you made? Well, we know we've got our work energy balance equation. We have the mechanical energy, so I'm just going to call that U1, plus the work gained between 1 and 2, minus the work lost between 1 and 2, equals the state in 2. Now what's the potential energy in the system at point 1? What's the potential energy in the system at point 1? Sorry? yeah, we've got a mass hanging down, m2, yeah, times by g times by h is obviously the potential energy in the system, okay? So we know that U1 is starting at rest, so the kinetic energy is 0, okay? U1 we know is m2 times by g times by h, the distance moved. What's the work gained as the system processes? Is there anything happening, any forces acting on that system, external to what's currently there? No, friction is work lost, okay? Work gained is 0. Wg between 1 and 2 is 0. The work lost, okay, is going into heating up the surface with friction, okay, and we know that the work done due to friction is mu times by m1, because it's the friction of this block, times by g times by h, which is the distance that it moves, okay? Because it's connected by a pulley, we know that the height that the mass drops is the same as the distance the block moves. Okay, and we know that U2 is going to be the kinetic energy of the masses as they're moving, m1 plus m2 times by v squared. And the question is, what is this v? And so you plug these things into this equation, so we have m2 times by g times by h minus the friction, mu m1 gh equals 1/2 m1 plus m2 times by v squared. And so we can say, well, if we multiply this side by 2, so we have 2 times m2 gh minus mu m1 gh divided by m1 plus m2, divided by m1 plus m2, square root that equals v. And from this point, we can then plug in the numbers. We have 2. Well, m2 we know is 400 kilograms. G is 9.81. H we know it says move 2 meters, so H is 2. Minus mu, which is 0.2, times by m1, which is 200 kilograms, times by G, 9.81, times by H, which we know is 2, okay? That's all multiplied by 2, and we divide all of that by m1 plus m2, which is 200 plus 400. And we square root the lot, and we get v. And if you do the sums in your calculator, that should come out to be 4.85 meters per second. The last part of the question says, what assumptions have we made? Okay, what assumptions have we made? But what about this thing here, the pulley? What are we assuming about the pulley? That it's frictionless, exactly. That it's moving without friction, okay? And what about the fact that the block, what's the shape of the blocks? Yeah? The other thing we're assuming is there's no air resistance. We're in a vacuum, okay? Because those things will also contribute to our work lost between point 1 and 2. We have friction, okay, on the surface. There's also friction in the pulley in real life, okay? And there'll be some air resistance as well. Obviously, 4.85 meters per second, the air resistance isn't great, but it will make a difference. Small difference, but it will make a difference. So, in summary, the work done between point A and point B is the integral of the force multiplied by the change in distance, dr. Sorry, the dot product of those two things together. And that work done between A and B is the change in kinetic energy between B and A. By constant force, we know that it's just the force times the distance, which is easy. Against gravity, we know that's mgh. And against friction, we know that's mu, the friction coefficient, times by mg, times by the distance moved, delta x. If the force is being gradually applied, okay, varying uniformly with time, then it's going to be the average force times by the distance moved. And that leads on to the work done against the spring, which is 1/2 kx squared. The power we know is work done divided by the time taken, which we also know is the force times the velocity. And the units for power are watts. And then we've got energy. Gravitational potential energy, mgh. Strain energy, or elastic potential energy, which is 1/2 kx squared. Kinetic energy we know is 1/2 mv squared. And then the mechanical energy is the sum of all those energies added up together. And then we have the energy balance equation. We've got the mechanical energy at point 1 plus the work gained between 1 and 2 minus the work lost between 1 and 2 equals the mechanical energy at point 2. Right, and that's the end of the lecture.